Hi everybody. So last time we learned about the magnitude system and about how the apparent magnitude and the absolute magnitude are like the flux and the luminosity, and their difference gives me the distance. So if I can figure out the absolute magnitude, I can figure out the distance to these objects. The apparent magnitude I always get for free. That will always be given to you. So you don't have to worry about calculating that. What we're going to need to figure out is that absolute magnitude. So this time we're going to learn a couple of techniques for figuring out the absolute magnitude of some very special objects that we call standard candles. And standard candles basically come about because it's an object that we know its intrinsic luminosity. We know how bright it really is. We can figure out its absolute magnitude then. So if I see this object in a distant galaxy, I know what its absolute magnitude is. I can figure out the distance because I already know the apparent magnitude. Remember, I just look at it. So if I know the distance to that object, then I know the distance to that galaxy as well. So that's the technique that we're going to learn today using two standard candles, a Cepheid variable that I'll talk about in a minute, and then a type 1 supernova. So let's get started. Okay, so as I said, we're going to be finding large distances. You're going to need your tool 23. Looks like this. You're definitely going to want to have this out because we're going to be using these charts that you see on the page here. So have that out so that you can reference it, pause the video until you're ready to go. All right, so we know that if we're trying to find the distance to something, if it's closer than 200 parsecs, we can use parallax. And if you can use parallax, you want to use parallax. It will always be the most precise measure we have for figuring out the distance. You just take that parallax shift, convert it from the shift to the angle if need be, otherwise they may just give it to you. And then 1 divided by the parallax gives me the distance in parsecs. But if it's greater than 200 parsecs, then that shift's going to be too small to measure. I'm not going to be able to do that. So you guys know from last time we need to use the distance modulus. That's the 3-step process to solve it. Just as a reminder, little m is the apparent magnitude, big M is the absolute magnitude, d then is the distance in parsecs. So calculate the value of the fraction, take the inverse log, multiply by 10. Done. Same way every time. So to use the distance modulus, we need the apparent magnitude. Well, that's easy. You'll look at the star. Now, you may be looking at it through a telescope, you may be looking at it with your eye, you may be looking at it with some instrument, but you always get that for free. You never have to calculate the apparent magnitude. Finding the absolute magnitude is a little bit harder. And so that's what we're going to talk about today. If we can find, there are certain objects that we call standard candles that we know their absolute magnitude. So if I see that object there and I'm able to recognize that that is that type of object, I immediately know its absolute magnitude. Well, I get its apparent magnitude for free, so I can calculate its distance. So the two that we're going to talk about this time are called a Cepheid variable, which is kind of a pulsing red giant, and then the second type is a type 1 supernova. All right, so Cepheid variables are not, they're pulsing, but not because they're about to become a planetary nebula. They're not about to just, puff off their outer layers. Don't get confused with that. This is one that's right on the border between convection dominating and convection not dominating. Now, for most red giants, we get ash builds up in the core, convection takes over, blows up to a big size, and it just sits there fat, dumb, and happy until something new starts to fuse in the core. In this case, though, the star gets big, but it's right on the border. So as it gets big, that gas gets thinner. And so the energy, the radiation, can actually pass through. Well, when that happens, convection is stopped. When convection stops, then, it shrinks. But as it shrinks, the gas gets thicker, and then the energy can't get out. So convection takes over again, and it gets bigger. And the details, the nitty-gritty details of how all of this works is what you'll be doing in the lab for this week. But that star then pulses just because it's right on the edge between convection taking over and convection not taking over. So it looks something like this. This is the light curve. This is the characteristic light curve of a Cepheid variable. So if you're observing, for example, a galaxy, and one part of the galaxy is the light from the galaxy is giving you this particular kind of light curve where it gets brighter and then dimmer and then brighter than dimmer. You may not can see the actual Cepheid variable, but you know that it's there because you can see the light curve from that. So if I can recognize this, then I can know, hey, there's a Cepheid variable there. I can actually figure out what the absolute magnitude is. Now, for the apparent magnitude scale here, remember the smaller numbers mean it's brighter. So the brightness is up at the top. This is the brightest point. This would be the dimmest point here. And then pulsation periods of a few days is pretty normal for that. So Henrietta Leavitt in 1908 discovered that there was a relationship between the period, the time it takes to go from here to here, from maximum brightness to maximum brightness, and the size of the star, which therefore means the brightness of the star. So if you think about it, a shorter period means it's going to be a bigger star. Well, because we're sitting here, we're pulsing a lot faster with that shorter period. We've got more mass to make us fall. So a bigger star is going to be a brighter star. So there is a relationship then between the brightness of the star, the intrinsic brightness, the luminosity, the absolute magnitude, and its period. And so she discovered this thing called the period luminosity relation. And we've got a graph for you down here at the bottom that we'll show right here. There's two ways you can use this. You can use the graph itself if you don't want to do any math. And just make sure that you're reading it correctly. This is a logarithmic graph. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But then this is 20, 30, 40, 50, 60, 70, 80, 90, and 100. So you find the number of days for the period. Let's say that it was 8.5 days. So this would be 1, 2, 3, 4, 5, 6, 7, 8. And I just made that up. So, and then you come up, see where it hits the line, and then read off the absolute magnitude. Now there's another way that you could do this. If you want to do a little bit of math, you can actually get a little more precisely. You just put in the period in days, so you put in 8.5. Now here we are actually taking the log. So you'll put in, on my calculator, I put in 8.5 and hit the log button. On your calculator, it might be hit the log button and type in 8.5. I don't know how it's going to be. Come by Live Help and we'll figure it out for your particular calculator. But so log of 8.5 times negative 2.7 minus 1.35 then gives me the absolute magnitude. You get the exact same thing that you get by going up, seeing where you hit the line and coming across. It just allows you to be a little more precise and get, maybe even 3 significant digits out of it. So I need the absolute magnitude. I get that using the period luminosity relation, whether I use the formula or the graph. I also need the apparent magnitude. Now, it's a variable star, right? So its apparent magnitude is actually changing. It's getting brighter and dimmer and brighter and dimmer. And you can actually see this. Delta Cephei, which is the first Cepheid variable that was ever discovered, you can actually see it with your naked eye getting brighter and dimmer and brighter and dimmer. And then by comparing to the stars around it, you can figure out its period. My brother did this in Cub Scouts in 5th grade, so you can too. So, but I need to know what that apparent magnitude is. So what we're going to use is we're always going to use the average apparent magnitude. So you read off the number up here, figure out what it is. That's not 4.3. That's going to be about 2.9 or so. Don't get confused. Do you see that? We're increasing this way. So it's not 4.31, it's 2.9. That's the biggest place that people are going to make mistakes. Be warned. Make yourself a note on your class notes. So this is like about 2.9, maybe 2.8. It's kind of hard to see from where we are here. Look on your own chart, you'll see it. And then this might be, I don't know, hard to read again, maybe 4.77, somewhere in there. So you add those two numbers up and divide by 2. That's going to be the average apparent magnitude. You'll use that for your little m. So let's take the example then that we have right here. So figure out the period. So all you need to do is take the top peak, see what day that occurs on, make sure that you're getting it to the nearest decimals, to the nearest tenth. Don't tell me it's 2 if it's actually 2.5, things like that. And then go to the next peak. So from this peak to this peak, and then subtract those two numbers, and that will give you the period. Pause the video, look at your own graph, and figure that out. All right, so when I do that then, I get a period of about 9.5 days. See if that matches what you have as well. And we're going to be filling in all of the data that's on the back side of your class notes here. All right, so the next step is I need the absolute magnitude. Well, so you take that period then, and we put that into the period luminosity equation, or you can use the graph, either one. And what you should find is you get negative 4.07. I'm going ahead and giving that to you because this is probably the hardest part of what we do for this particular section. So pause the video and see if you get negative 4.07. Okay, if you use the graph, you might have gotten negative 4.1, which is fine, but it means your numbers will be slightly different from what I have from here on out. If you put it into the equation, you should be getting negative 4.07. Let's see how we can do that. So the equation is printed on the page there. So we have 9.5, and on mine I hit 9.5 and then log. You might hit log in 9.5, I don't know. And I get 0.9777, okay? Multiply that by times 2.78 with a negative sign. Make sure it's the negative sign and not the subtract button. And I get negative 2.718. And then finally, I want to subtract 1.35, and I get negative 4.07. Okay, so make sure that you get that as well. That's probably the only hard part to everything that we're doing here today. All right, so looking at your chart then, the next step is to get the maximum apparent magnitude. So read this off of your graph here and read it as precisely as you can. Get it to the nearest, hundredth or so. Pause the video. Okay, so I'm getting 4.29 for my maximum apparent magnitude, and my minimum apparent magnitude, which remember is going to be a bigger number, I'm getting 4.78. See if that matches what you get as well. Okay, the next thing I need to do is take the average of those. So you just add these two numbers up and divide by 2. Go ahead and do that now. Pause the video. All right, when I take the average, I get 4.54. Now here's a tip. It will always be halfway in between these two. So if you get an average that's not in between these two numbers, you did something wrong. Go back and fix it. So this is my little m. My little m is 4.54. My big M is negative 4.07. Now I'm ready to put that into the distance modulus, and I can figure out what the actual distance to this star is. So what I want you to do is pull your class notes out from the previous lecture. So from the one on magnitudes, where we show you how to solve the distance modulus. That will take you through all the steps. But now use negative 4.07 for the absolute magnitude, use 4.54 for the apparent magnitude. Pause the video, do that now, then we'll come back and do it together. All right, did you really do it? If not, seriously, you're going to want to stop and do this. Okay, so step 1, do little m minus big M, divide by 5. So little m is 4.54 minus 4.07 negative. I get 8.61, divide by 5. So for step 1, I get 1.722. Step 2, take the inverse log. On mine, I just hit second function log, and I got 52.7. And then finally, multiply by 10. And when I do that, I get 527 parsecs. So you see that I can measure the distance of something that is much greater than 200 parsecs, because Cepheid variables, that curve is very easy to recognize. Even if I can't see the actual individual star, I can see that the light from that part of the galaxy is changing in just the right way. Okay, that's how we use a Cepheid variable to find the distance. The other standard candle is actually much easier to use. It's called a type 1 supernova. Now, we talked about this briefly when we talked about star formation or star death. When I have a core collapse supernova, the one that would blow up and become a black hole and a neutron star and things like that, that was a type 2 supernova. If you remember from that lecture, a type 1 supernova is a binary white dwarf. So I've got these two white dwarfs, these two husks of dead stars. If they spiral in and collide with each other, the pressure on the surface of the star, on the surface of the white dwarf, it's not really a star anymore, but the pressure on that can cause that carbon to fuse. Remember, the white dwarf is made out of almost entirely carbon. So when that happens, remember that the white dwarf is being supported by electron degeneracy. Those marbles are stacked. Think about the rule. When I have fusion in the presence of electron degeneracy, the temperatures go crazy. But now, instead of being protected inside the object, it's actually on the surface. This causes an uncontrolled reaction that blows the star apart and forms a supernova. Now, this is not the type 2 supernova that we talked about before. It's got a different light curve, but it's still one of the brightest explosions in the universe. We can see these all the way at the edge of the universe. We always want to use a type 1 supernova if we can, Problem is they're pretty rare. So we get so excited when, astronomers are about to pee their pants when they see one of these things go off, because now we can actually measure the distance. Well, since these things are all made by the same thing, a binary white dwarf collision, they all have exactly the same absolute magnitude. So this is a typical light curve from a type 1 supernova. This one happened in 1994, and this is the apparent magnitude that we're looking at here. All you need to do for the type 1 supernova is find out what its peak magnitude was. So its peak magnitude in this case might have been, and that's a little hard to read, but maybe 13.2 or something like that. You read it more carefully using your chart down here at the bottom. So the apparent magnitude you get just by reading it off. Notice that you do not have to do any kind of averaging. But here's the fun part. The absolute magnitude of that peak is always negative 19.3. No math to do, no calculations, no nothing. It's just negative 19.3. So that's a good number to memorize. So that the peak of that type 1 supernova, its absolute magnitude is negative 19.3. Here I'm getting an apparent magnitude of 13.2 or so. So little m is 13.2, big M is negative 19.3. Put that into the distance modulus, and you can actually get the distance from that. So we don't have you do that on the sheet, but it's probably worth doing. So let's go ahead and do that right quick. We're going to do that one together. So let's suppose, see if I can read that a little more carefully. Let's suppose it looks like maybe it's about 13.1. So let's go ahead and use that. So little m is 13.1 minus big M, which is 19.3 negative. I get 32.4. Divide by 5. All right, that's step 1. I get 6.48. So let's work out the fraction. Next step, step 2, is take the inverse log. On mine, it's second function log, and I get, let's see, looks like about 3 million, so about 3.02 times 10 to the 6th. Make sure that, yeah, about 3.02 times 10 to the 6 parsecs. Or not parsecs yet, we need to multiply by 10. And so I get 3.02 times 10 to the 7 parsecs. So this type 1 supernova occurred about 30 million parsecs away. That's a long friggin' way. Yet because it's so bright, I'm still able to see it. 13th magnitude is easily within the range of our telescopes up at GCC North. Now sometimes we're also going to need to find the absolute magnitude, and you're going to need to do this in the lab. So we need to talk briefly about this. Let's suppose that I got the distance using the parallax, and I know the apparent magnitude because I just looked at it. I can use the distance modulus to also find the absolute magnitude if I want to use it for something else. So we solve the distance modulus for m, and it comes out in this form right here. I've just rearranged this thing to solve it for m. So you multiply both sides by 5 and then subtracted the big M to this side, the log on this side. So this formula you can use if I know the apparent magnitude and I already know the distance. The only way I could get that would be if it were close enough that I could find it with parallax from that. So in the lab, you will be using this formula. So it might be worth jotting down, making sure that you've got it. All right, so that's where we're going to stop. So make sure that you download the practice worksheet. Looks like this. We're going to have you use both a Cepheid and a type 1 supernova, and you're going to figure out the distance to both of those. If you have any questions, make sure you come in live help. So now you know how to find the distance to these two standard candles, the Cepheid variable and the type 1 supernova. Now, yeah, that's great because I can find that distance, but the key thing is that usually those two objects will be embedded in something else. Either it'll be, some group of stars on the other side of the galaxy, or more often it's a galaxy way out at the edge of the universe. So if I get lucky and I see a Cepheid variable, or even more lucky and I have a type 1 supernova, then I can actually get the distance to these galaxies. And that's how we end up measuring the distances to the edge of the universe. We'll be doing even more with this later on when we start looking at Hubble's law and the expansion of the universe and actually finding that edge with that. We'll see you then.